There are also a lot of people now that are coming back to the natural aspirated with very high revving, with very good noise, with very good power delivery. Beautiful to drive, not just to destroy the new world record in the speed or in the 0 to 300 kilometers,
Welcome to the HPA Tuned In podcast. I'm Andre, your host, and in this episode, we're joined by Riccardo from Italtecnica from, you guessed it, Italy. Italtecnica is a company that is involved in the design and manufacturing of bespoke engines. They're a very low production rate engine supplier, and this is quite rare. It's not that often that we get to talk to someone that's this involved in the design process of bespoke engines. So we decided to take this opportunity to leverage some of Riccardo's knowledge and see what we could take away from this that we as mere enthusiasts can then apply to the modification of existing OE production engines, which is what we tend to do. In this episode, we find out about Riccardo's background and how he actually got involved in engine design in the first place. Let's be honest, it's not exactly an easy career to get into. We then talk about some of the aspects of engine design that I know there's always a lot of controversy around and a lot of misunderstanding. For example, compression ratio, how important is it, and how do we balance the compression ratio of our engine versus the knock sensitivity. We also talk about rod to stroke ratio, which again is a very misunderstood term, I believe. Talk about rod to stroke ratio and its importance and when we should, if ever, be looking to try and optimize or modify that. Likewise, bearing clearances. Again, there's a lot of argument and debate about what we should be doing with bearing clearances. And admittedly, when we're looking at a bespoke designed engine for a particular purpose, the bearing clearances for that application may be a little bit different to what we need when we take a stock engine that makes 300 horsepower and revs to 7,000 RPM. And now we want to make 1,000 horsepower and rev it to 11,000 RPM. Regardless, we talked to Riccardo about the ins and outs and what we need to know. We also talk about cylinder head design because really this is where the airflow in and out of the engine comes from, and optimizing this is where the engine's power comes from. There's a lot to understand. We talk about valve actuation styles and the pros and cons of each. We also talk about the consideration for road legal engines of emissions and how that's likely to impact the power production of the engine. So there's a lot packed into this particular episode. Before we jump into our chat, for those who are new to the Tune In podcast, High Performance Academy is an online training school. We specialize in teaching people how to build performance engines, how to tune EFI, how to construct wiring harnesses. We also cover topics on fabrication, 3D modeling and CAD, race driver education, and data logging, just to name a few. You can find all of our courses at hpacademy.com/courses. All of these courses are delivered in high-definition video modules that you can watch from anywhere in the world, provided you've got an internet connection. This means you can learn from the comfort of your own place and you can learn at your own pace. All of our courses also come with a 60-day, no questions asked, money-back guarantee. So if you purchase them for any reason at all, decide it wasn't quite what you expected, no problem, let us know. We'll give you a full refund. And for podcast listeners, you can also use the coupon code podcast75. That will get you $75 off the purchase of your very first HPA course. We'll put the coupon code in the show notes to make it nice and easy for you to find. Lastly, if you like free stuff, then I've got a great deal for you. We are constantly partnering with some of the biggest names in the aftermarket performance industry to give away some great prizes. You can always find our latest prize at hpacademy.com/giveaway. It might be an aftermarket ECU or dash. It could be some engine components or engine building tools or just about anything in between. They are great prizes and we will ship them free of charge to your door if you're the winner. There's no tricks here, no purchase required to get your name into the draw. All right, enough with our introduction. Let's get into our interview now. All right, thanks for joining us today, Riccardo. And as always, let's start by finding out a little bit about your background and specifically how you got involved in engine development and an interest for cars in general.
Yes, let's say that I started doing the mechanical, training. So high school, I was in the scientific lyceum, so in the technological department of studies. But actually, I was not born here in Turin, in Piemonte. I was born near Venice, and then I have to choose the university, and I was about to choosing the Padova University, which is quite near me, my home, which is where all the guys like go, because it's a big university, also quite important. But then I saw that there was in Turin the automotive university, automotive engineering, and then I got interested in that, and I said, why not? Why just don't go there and see if I am also interested in cars and in engines and in all this kind of stuff.
So hold on. You chose this automotive based university, and then developed an interest in cars and engines. It didn't sort of go the other way around.
Yeah. It went more or less like this. Yes, I mean, I not that I was not involved in nothing, but I was more involved in physics, mechanics, but more in a general way. Then I found like an application of this in cars and engines, and
Okay, interesting. Yeah, I would not have picked that. All right, so at the time you decided to go to this university, what did you sort of have in mind as your career trajectory? What did you sort of think you were going to come out of this university and end up doing? Obviously, I'm sort of where I'm going with this is obviously automotive in general is a very broad range of topics that you could be involved in.
yes, that's what you think when you go to the university. It's so wide the ambient you are looking at, that it's very difficult to say, okay, I will be that in that specific branch and that specific topic, especially in automotive, where you have a variety of things you can do completely different. You can do engines in the mechanical way, you can do engines in the electronic way, you can do vehicle construction, you can do racetrack engineer, you can do basically everything. You can do salesman for automotive companies. I have some friends that did that, but I was more focused on the mechanical parts and on the engines part, because they represent the truly engineering, I think, in the car. So I went for that. Yeah.
Could you give us a sense of some of the topics that you were covering in this degree?
Yes, but well, first in the first 3 years, it was like mechanical engineering, so general mechanical stuff, and then in the specialistic degree, it was more like on the engine. So it was engine design. It was combustion systems. It was everything, yes, related to components design and also manufacture, and emissions on the last years. It was emission courses, which are very important, very relevant on the for the world we live in today.
Definitely. Becoming increasingly important.
Yeah. Also, when I did it like 5 years ago, there was already something for hybridization and electric motors, which I know now that that took the major part of the courses, the electrical part of the car.
Okay. Once you graduated, what's your work career looked like? Have you had other positions before getting employed by Italtecnica?
Well, no, I didn't have any working positions for company. I worked 1 year, let's say, for the Politecnico, so for the university itself, as let's say a researcher in a project that was the continuation of the thesis project, and I went on with that project for 1 year. In this project, we were collaborating with Italtecnica, so I knew them on doing that project, and then I asked them if I could enter. They asked me if I could join them, so it was like
A match made in heaven.
a match. Yeah.
Okay. Let's talk about Italtecnica in a little bit more detail. Can you give us a bit of an understanding of the business? So let's start with maybe a brief history. Where did this business come from?
Yes, it came from the owner, Mario Cavagnero, building his own company because he was working on another company before as the chief of the workshop in Conrero, which was a very known Opel racing car developer for Opel. And he started his own company in 1985, Italtecnica, and he started collaborating with Peugeot Sport for the rally cars. And so this collaboration, it was the end of the 80s, start of the 90s. It was the rally was going very good, and Peugeot Sport was going very good, so the business grew quite fast. But then the rally suddenly, let's say, dropped a lot in the end of the 90s, and so Mario had to change a bit its strategy.
At this time for Peugeot, was this about engine development for Peugeot Sport for their rally program?
It was not really engine development. It was more like a vehicle construction and setup for the racing, because everything was given by Peugeot. And I'm not sure if here we made some modifications on something, on some components, but it was more about following the cars on the racing, and setting up the cars for the racing.
Okay.
And then it started the collaboration with Ferrari and Maserati, especially with Maserati Corse, with which they developed the Maserati MC12, the iconic racing car with a V12 naturally aspirated. It was co-developed here in Italtecnica on our test bench with the Maserati Corse that was designing the engine, but we were, let's say, helping them in optimize it. And then we started a collaboration, very big collaboration with General Motors in the early 2000s, because they were doing diesel engine calibration and also testing of different components like connecting rods, pistons, valves, valve trains. And they made us build 7 test benches for them. We were running like 24 hours a day.
Wow.
So, and we still have 7 test benches here.
Sounds like quite a lucrative contract.
Yeah, yeah. We were working 90% for General Motors. And then it went on for 15 years. Then in 2019, after the Dieselgate made its effect of destroying a lot of things,
Yeah.
and here in Turin, General Motors had the division of diesel department. From one day to another, they say, "Oh, we don't do this anymore," and okay, you go on by yourself.
So business went from 100 to 0 pretty much overnight.
Yeah, yeah. And then there was the COVID. So from 2018 to 2020, it was very, very difficult years. But in 2020, the good things is that we started with the resto-mod project, which is the Kimera Evo 37, with which the company Italtecnica reinvented a bit its competencies. Let's say we came back to the engine design, and with the son of Mario, Carlo, which is my colleague, is 32. I am 30, so we are quite the same age, and he is embracing the all the activity. I mean, Mario is still here and is still very very strong, but Carlo is taking the company, especially the engineering part. And we are doing these resto-mod projects, and we started with the Kimera Evo 37 with the 4-cylinder engine.
Now, people will be able to find some information about this Evo 37 on your website, but can you give us a quick rundown on what this is for those who haven't sort of studied the website just now?
Yeah, the Evo 37 basically is one of the first and I think the most successful resto-mod project, which means that you take one iconic car of the past, in this case is the Lancia 037 Rally, Group B rally car, and you redesign it in a modern way, so to have a modern engine, modern chassis, modern aesthetic, and comforts, and you put it on the market like that. Of course, it's very expensive. It's a niche market car, but it's a reinvention of the old icons that it's a bit of the lacking market that there is today. So OEMs now don't put on the market this kind of cars, and there are some companies like Kimera that started to fill this gap that was present. In fact, a lot of companies now do that, and we started with them with this car. And yes, it has a four-cylinder, reminding a lot like the original 037 car, but this one is a turbocharged plus supercharged. The old 037 was just supercharged, so this has more power.
Let's just talk about the engine for a moment. This is kind of relevant to my interests as I actually currently have a Ford RS200 Evolution sitting on my dyno. And particularly here in New Zealand, you don't get to see Group B rally cars, never mind actually tuning them. So that particular car is a four-cylinder turbocharged 2.1 litre. And it's been actually resto-modded essentially as well, in that it's got a suite of modern electronics, being Motec ECU dash PDMs. It's got a modern Garrett ball bearing turbocharger. The engine itself, however, is still pretty well as it rolled off the production line. And straight away, just knowing what a Garrett G30 900 turbocharger is capable of doing on an engine of circa 2.1 litre, you can tell that the cylinder head probably is not that efficient given the amount of boost that I had to use to make 500 wheel horsepower. So in taking a resto-mod approach from a Group B car from the 80s, what do you change in the engine? How do you design a better mousetrap essentially?
We changed everything. The engine was made from scratch on the new car. At first, we started on the first, I think, three engines by taking some original design castings. I mean, the casting were new, but on the original design, to maintain the for especially for the block, to maintain the originality of the project. But then it was very heavy, the block, and it was quite difficult to adapt all the accessories we had to adapt, and all different layout that we had to comply with. And so we went with remaking the block. Of course, the cylinder head is aesthetically is the same from outside, but inside is completely re-engineered, so it's much more efficient. And
just in terms of the cylinder head, the way I sort of always consider an engine is the block essentially is there to support the power. It's basically just a big pump. And realistically, the amount of power that we can make is going to be dictated by the airflow in and out of the cylinder head. So what has changed, I guess, from the 80s and 90s to modern era in terms of the approach to designing a cylinder head? In other words, how are we making more power with a modern cylinder head design, and what did they get wrong back in the 80s?
Well, I think back in the 80s, well, things were much less efficient. Let's say also turbochargers and all these machines. Parts, let's say, they were not maybe machined as well as we are doing today. Maybe if, now I don't remember the 037 car, but I can't remind if it was machines, the ducts inside the head, or just casted. But yes, it was different conceptions of imagining this pumping capability of the engine, I think. I mean, the theoretical stuff, it was there because they knew that there are pressure waves and all this kind of stuff, and that if you make the correct size inlet ducts and exhaust ducts, you can gain more power. But I think also the computational power was very low, and maybe it was much more trial and error on the real parts than on doing the simulations from the beginning and doing the correct dimensioning from the beginning. So I think in that doing that, you lose quite a lot along the road. I think that is, I think, the main difference.
Yeah, I could assume that back in that era, designing the engine virtually using CAD and CFD probably Probably wasn't there. Manual computations and probably a whole lot more prototyping and testing, which obviously gets labour intensive and incredibly expensive. So we probably live in a much easier time these days with the technology that we've got available, which is obviously also what we're going to dive into. So to bring us up to speed, we've talked about this resto-mod Kimera engine. Current era 2025, what sort of engines are you offering, and how do these get driven, I suppose? And what I mean by that is it a case of a customer coming to you with an engine project in mind, you developing that engine for the customer, or are you seeing a gap in the market for a particular engine platform, developing it and sort of a build it and they will come mentality?
No, for the moment, it was always the customer coming to us with a project in mind. And so we had to design the specific engine for the customer. For example, the Kimera, it was the first. Then we have the Totem V6. Then we have the Nardone V8. And then we have the Jamar V12 engine that is now just produced. And so we had a lot of different projects keeping us very very busy in the past few years. And now we are seeing some opportunity in creating our own engine, which will be V12 natural aspirated, and we will present it in November. And yes, just now we are thinking about offering our own engine off the shelf, let's say, without having a project behind to support it, let's say, without being proprietary of someone in a project.
Mm. Coming back to your naturally aspirated V12 project, so obviously I can only assume this is going to be a very expensive engine for a customer to purchase. When you're coming up with a concept like this and you're going to bring that to market, what is the use case that you see for that naturally aspirated V12? Is this going to be for perhaps a race series, a controlled class, or someone wants to build a one-off project and just wants an amazing sounding engine, or is it a combination of all of the above?
Yes, it's more like that, let's say, one-off projects or a few numbers, supercars, hypercars. We are now targeting more like homologation, so homologated products that will run on the street as new cars, compliant with emission regulations and everything, because we think in that field there is a gap that no one is following, because in the racing there are a lot of engine producers, and I don't want to say that everybody can make an engine and go for the racing, but it's much more, let's say, easier, and there are much more names out there that can make that kind of service, let's say. But we are more targeting the company that wants to put a company or person, a small number of people that come to us and say, we have this in mind, we want to realize this supercar with this project with that is street legal, that we can run with a reliable engine. And so that's the kind of target we have now and for the future projects.
If you're a fan of the podcast and you're interested in topics like engine tuning, automotive wiring, performance engine building, 3D modeling in CAD, or anything else in the high performance industry, I have something that you might be interested in. Introducing the High Performance Academy VIP package. This package of courses gives you lifetime access to all of HPA's online training for one price. These courses cover everything from tuning and reflashing petrol and diesel engines through to motorsport wiring, engine building, fabrication, design, car setup, and plenty more. Right now, you can get $500 off High Performance Academy's VIP package using the code podcast500 at checkout. Becoming a VIP means you'll never pay for another course again. You'll get instant access to all 40 plus courses we currently offer, plus every new course we ever release in the future. Want to define maps or tune with WinOLS? Curious about CAN bus devices or how CAD can help make your dream build a reality? These in-depth topics, as well as many others, each have their own dedicated course that are going to help you master whatever it is you want to learn. And as a VIP member, you're not just getting the courses, you'll also join HPA's online community with lifetime access to our member forums and members' webinar lessons. Again, the code is podcast500 for that $500 discount. Just head over to hpacademy.com to check out the full VIP package and everything it contains. All right, let's get back to the episode. Okay, a bunch of things that I want to dive into there, but before we do, just a little bit more detail about this V12. Obviously, it's a project and idea only at this stage by the sounds of it, but can you give me sort of some numbers around what you'd expect in terms of power output, RPM range, etc.?
Yes, we will have basically two versions on our mind. The first one will be homologated version. It's a 6.7 liter, and it will be homologated version going to 9,500 RPM with 850 horsepower, and another version going to not homologated, thought to for the racetrack, going to 10,200 RPM with 900 horsepower. So basically, these are the two versions we are thinking about now. So we keep always a door open in the both the categories: homologation for street use and racetrack use.
Okay. The numbers are certainly impressive. On that note, though, I kind of see there's been a trend with the supercar and hypercar market realistically these days where the numbers just keep spiraling out of control. I think almost the naturally aspirated engine, with very few exceptions, is a thing of the past. Turbocharging in north of 1,000 horsepower is kind of, if you want to get anyone interested, is kind of required. I personally don't see 1,000, 1,200, 1,500 horsepower really being that useful for a street-driven car in most instances. So to me, it's a moot point. But how do you weigh that up when the demand is, or the expectation, I guess, is more than the demand? The expectation is 1,000 plus horsepower. Turbochargers are obviously an easy way of achieving that. How do you sort of reconcile that with building a 6.7 litre naturally aspirated V12?
Well, because we saw that not everybody likes turbocharged and a lot of horsepower just to throw it on the street and destroy the tires and all that things. But there are also a lot of people now that are coming back to the, let's say, the V12 engines, or maybe also not V12 but natural aspirated with a very high revving limit, with very high sound pitch, with very good noise, with very good power delivery. Beautiful to drive, not just to destroy the new world record in the speed or in the 0 to 300 kilometers,
I think you've kind of just hit on something there that I think is really important. These hypercars where you're spending $1, $2, $3, $5 million doesn't really matter. For the most part, these cars are probably going to do no more than 500 or 600 kilometers of use a year. Probably the majority of them aren't going to see a racetrack or be used how they're intended. And at that point, it doesn't really matter how much power they've got. So I think you've got to also focus on the other aspects of the engine that's going to bring enjoyment to the person who's just shelled out all of this money. And a lot of that is the oral sensation, what the thing sounds like. And I mean, I think Gordon Murray's probably hit the nail on the head with that one with his T50. You listen to that thing on YouTube or running up the hill at Goodwood. I mean, it just takes you back to the naturally aspirated F1 era. So I think there's a lot to be said for the whole package, the sound of the engine. Yes, it still has to have high specific power, but 850, 900 horsepower is obviously plenty. You just don't get that sort of sound with turbochargers, I don't believe.
Yeah, you don't get that kind of sound. And if you think about that, 900 horsepower 20 years ago, it was like already on over the top of everything apart the Bugatti Veyron maybe, but it was the top of that you could have. And so now you think that it is quite a normal supercar, okay, 900 horsepower, not so much, But if you think about that, 900 horsepower maybe on a light car and very responsive chassis, it's something that not so many people can drive and can appreciate in its limits, let's say.
Yeah, no, absolutely. Just with my reference back to the T50 from Gordon Murray, obviously there's some parallels that I can't help but draw here, and I don't know a lot about this. Just while we've been talking, I just quickly had a Google to refresh my memory. So he's used a Cosworth-based V12, which is bespoke for his project, and I think 3.9 litres and the 12,100 RPM rev limit. When you're dealing with a naturally aspirated engine and you want to make a lot of power, realistically, RPM is your friend because it is a multiplier of torque. So if we can get airflow at high RPM, that's how we're going to make a lot of power, which is why the very small capacity Formula One engines were still up at that sort of 850, 900 horsepower mark. On that note, so how do you sort of decide on what a realistic RPM rev range is going to be for an engine like this? Why settle on 10,000? I think you said 10,200 RPM for the race one.
Yeah, 10,200. Yeah.
How do you decide on this? Because the other aspect is, as the RPM range increases, the stresses involved do also increase, so you've got to think about component reliability and longevity as well.
Yeah, that's basically the one of the main drivers of the rev range choice. I mean, of course, you have to go up with the power to reach a good power with a naturally aspirated engine, but then you have to realize that you are creating an engine that needs to be road driven with a certain reliability and with certain comfort also for the passengers. So deciding the correct RPM range is always a big trade-off between how much power do you really want, do you really need for that kind of application, and instead how much will be appreciated the engine for its reliability, for its low RPM torque, for its all the other things that are not pure power at the top end. And depends on the application, but for a road legal car, already 10,000 RPM is quite a lot. Yes, Cosworth went to 12,000, but they are Cosworth, and basically they can do that.
The other consideration here that I assume comes into this, and this is sort of more around your homologated emissions compliant engine design. So in order to get torque at high RPM, we need airflow, and usually this comes down to your head design, your ports, and a big driver of this would also be cam design as well. Where I'm going with this is generally a cylinder head that's going to flow really well at 9, 8, 10,000 RPM. I would have assumed is going to be very difficult to be emissions compliant. So again, talk to us about that trade-off.
Yeah, well, if you want to have very high airflow at high RPM, you have to do very big intake ducts, especially intake. Yes, also exhaust that follow, but the intake ducts must be very big and very straight if you want to have a lot of power at the high RPM. So you start maybe from saying, oh, this is the best I can do for the power. So very strict ducts and very wide, very big valves, very big ports. And then you have to go back and saying, okay, if I want to pass emission regulations, I need very good combustion efficiency, so very good mixture preparation, so very good, let's say, turbulence inside the chamber. And you would like to have less airflow, maybe faster airflow at low RPM, so smaller valves, low port velocities, and you have to find a good trade-off between that. A good help now comes from the new studies for the tumble generations, so for motions inside the cylinders. and these they can be simulated also with software. So basically, you try to, while having big ducts, you try to enhance the combustion stability and speed also at low RPM by creating more velocity inside the cylinders with tumble motions. And that is basically how you can deal with having a good head for the higher flow on the high RPM, and a good head also for the emission compliant, for the emission regulations. Yes.
So you've got two design criteria that are almost at opposing odds at each other. Safe to say that designing an engine like this, where you have to retain emissions compliance, is going to be dramatically more difficult than a non-homologated race engine.
Yeah, that's incredibly more difficult because well, if you have to design for power, you just do things as straight as possible, as big as possible, as much as possible of everything, and you have as power as possible. As you If you are able to do that, you can obtain very good numbers. But if you have to homologate, you have to know what happens inside the cylinder. You have to know how to obtain the homologation, so how to avoid the pollutants formation and all this kind of stuff. So it's much more difficult, and combining the two things is the most difficult part, of course.
Yeah, yeah, absolutely. How about the use of technologies such as variable valve timing with an engine like this? Is that something you're leveraging?
Yeah, of course. Now it's mandatory, I think, to have variable valve timing. If you want both of this, so power and emission compliant, you have to do variable valve timing because at low RPM you want to have almost zero overlap between intake and exhaust, so you don't have gasoline flowing out in the exhaust or unburned going out in the exhaust, and so you retard a lot the intake usually, and then you have to adjust the timing, of course, going up in the RPM. When you are outside of the emission control, you can look for the power, so you adjust the timing for the maximum power. But when you need it for emission control, at example at the idle or light load, you really need to do a good work with variable valve timing. Yes.
Yeah, okay. I'm interested in just bringing in another topic that you may or may not be leveraging here, something that I think probably many of our listeners probably haven't heard of, which is Atkinson cycle. And at a very brief high level, it's essentially a design of engine where the intake stroke is reduced in comparison to the exhaust stroke. So mechanically achieving that is very complicated. The idea behind it is that we're reducing the amount of air and fuel ingested into the engine, so we're actually reducing specific power output, but we're actually gaining efficiency because of the increased expansion stroke. This can be achieved to a degree with variable valve timing as well. Is this something that you leverage with your emissions compliant engines?
Well, we are well aware of that. Let's say that this strategies is used for lowering the CO2 emissions because the engine is more efficient. So more efficient means that it consumes less fuel, so it produces less CO2. And but since we are producing a very very low number of engines, let's say that CO2 is not something that we are very strict about. Basically, when you play with the valve timing, you are playing with the Atkinson cycle, in which the expansion stroke is longer than the compression stroke, so the engine gets more efficient, and you obtain that by retarding the intake. So you have the dynamic compression, let's say, lower than the actual expansion of the engine. But let's say that we don't target that specifically, but we obtain it as a side result by doing the variable valve timing to pass the emission test, let's say.
Sure. So it's not necessarily a drive towards Atkinson cycle, but with the variable valve timing, you're able to achieve a degree of that, and then it's a case of optimizing the valve timing to give you the performance and emissions that you need to be legal.
Yeah, let's say that you target Atkinson cycle or Miller cycle, as you want to call it. If you are targeting low fuel consumption with very efficient engines, with more like OEMs are doing on the lower powered vehicles, let's say. Actually, I don't know if now they do it also on supercars, on maybe some strategies. But actually, on our case, we don't target it specifically. It's a side step. Actually, I think it's beneficial also in our engines, but we are not targeting it.
Okay. Just to, I guess, fill in the whole picture there for those who are fresh to this concept, as I mentioned, Atkinson cycle, you essentially got a different length intake and compression stroke compared to the expansion stroke or power stroke and exhaust stroke. And achieving that, obviously, with a fixed geometry crankshaft is not going to be possible. We're achieving this to a degree, the Atkinson effect, by retarding the intake cam so that essentially you've got your intake stroke, it's ingested fuel and air, but if you hold the intake valves open as the piston starts coming back up towards top dead center, we're forcing some of that fuel and air back out. So we've actually got less intake charge. So that's sort of how we mimic the Atkinson cycle effect using variable valve timing.
Yeah, that's one way to do it, or there are also other ways. By playing with the variable valve timing, you get also other ways that I think are also more efficient, because you don't push out the air to the intake, but you act like a spring inside of the cylinder. So you create a slight vacuum when you pull down the cylinder, and then you have to back up when it's coming up. But anyway, it's always to target that. Yes.
Okay. All right. I want to dive into some of the specific sort of parameters around engine design and just get your take on their importance and how you consider them. We're going to deal with them in isolation, but of course, when it comes to designing and building an entire engine, you can't do that. All of these concepts have to sort of come together and work in harmony. But we'll just cover some of the main topics that people will have heard and probably have to consider. Let's start with a really simple one, our compression ratio. I'm just interested, how do you sort of decide on a target compression ratio when you take into account fuel octane, maybe target power level and RPM range, and also, of course, if the engine is forced induction with supercharging or turbocharging?
Well, of course, now we are targeting for 95 octane on almost all our engines, because they need to be road legal. So at pump fuel is almost everywhere 95 octane. You can find also 100 octane, but you need to tell the customer that you really need to use 100 octane, and then you don't know when they put 100 and when they don't. So we design our engines on the 95 octane usually. And of course, the compression ratio, we have from experience some targets that we reach for the naturally aspirated engines and for the turbocharged engines. Of course, you make some simulations with 0-1 dimensional models, but let's say it's more like an experience thing, designing the compression ratio of the engine. Yes.
Okay. How important is the compression ratio in terms of power production? What I'm getting at here is, if we were to go from, let's say, a naturally aspirated engine, 10.5 to 1 through to 11.5 to 1, obviously it's going to be very dependent on a bunch of other parameters, but could you give me an idea, just a ballpark of what typically you would expect to gain in terms of percentage of power? Is it possible to ballpark that? Are we talking, a 1 point compression ratio rise might give us a 3% increase in power, or is it, 5%, 10%, or is it just not possible to ballpark like that?
No, I would say yes, around 5% is what I would expect in increasing from 10 to 11. I expect, yes, if the engine is resistant to knock and to everything, I would expect that. It depends on from what to what, because if you increase from 7 to 8 is one thing. If you increase to 13 to 14, the increase, the benefit is much less evident. I would say if you increase from 7 to 8, you have a lot more power. If you increase from,
So it sort of follows a curve as you'd expect, and the gains become iteratively smaller as the compression ratio rises.
yeah, the efficiency of the engine increases, but not so much if you are already very high in compression ratio. Yeah.
Sure. You mentioned this comes from simulation and also experience. I'm just interested with simulation in the virtual world. Are you able to simulate where the engine's knock threshold is going to be? Basically, can you work out with a degree of accuracy at what point the engine is going to become knock limited?
Well, the software could do it, yes. The difficult things is to set up the correct model for it, because these are, let's say, OEM studies, because to reach that kind of precision in the model, determining the knock threshold by software is a very demanding skill for the model that you set up. Because if just one parameter is not correct, you obtain results that are not precise at all. So the software is capable of doing that. It can do a lot of very, very good stuff, but we usually don't to simulate also the knock threshold on software, because we don't have the budgets and also the time to develop it. Because let's say that you would need to develop a real model of the engine that you design, and with that model put it on the test bench, and calibrate the virtual model on that engine, just to have the model calibrated on the software. So then from there you can start to improve, to modify, but you need to have a good base of the model, that it reflects the real engine, because there are a lot of parameters that really you cannot guess by putting it in the software and hope that they are correct. Yeah.
Sure. I guess that's, as you mentioned, a very complicated thing to model, and it sounds like it's another case of, with your simulation, garbage in, garbage out. So it'd be very easy to get misled if you don't have that model and all the simulation absolutely perfect.
Yeah, I think OEM world, they do that, I think, because they have of course, the budget, the time for developing the engine, and so on. And they go on developing the engine for many years also after it comes out. So they have much more power in doing that. Yeah.
Okay. All right, moving on. The next parameter I want to talk about is rod to stroke ratio, which there's a lot of debate about the importance, significance, relevance of rod to stroke ratio. Generally, for us in the aftermarket, what we can do with rod to stroke ratio is somewhat limited, because we're dealing with an OEM production engine block crankshaft. The geometry is fixed within reason. So for those who haven't heard that term, it is literally exactly what it sounds like, the ratio between the length of the connecting rod and the stroke. So the theory is that a longest rod to stroke ratio is preferable for higher RPM ranges. For a conventional road car engine, 7,000, maybe 8,000 RPM rev limit, maybe a rod to stroke ratio in the range of 1.5, 1.6 might be typical. For a sport bike, maybe a 14,000 RPM rev limit, maybe sort of closer to 2 to 1 or somewhere in that range. So is this important? Do you consider it? Should we be worrying about it as much in the aftermarket, or is this more driven by the other geometrical constraints of the engine design?
Well, in our case, from what I've seen, it's an important parameter, of course, because, for example, the shorter the rod is, the much more intense is the lateral push on the pistons and on the liners. And yes, that is one of the main characteristics. If you go very high RPM, you start having a lot of inertial forces pushing around, and having a short stroke is quite painful, I think, for the pistons and for the liners. Yes, we consider it, but in my opinion, it's not the driving parameter. I think we have a lot of different parameters, and one of them is the engine dimensions, which is if you make quite big engines as we do, every millimeter that you can shave, let's say, it's very good also in terms of weight. But of course, if you go high with RPM, it's a very good thing to have a longer rod because of what I said before. And in the aftermarket, I mean, if the OEMs already thought about that, I mean, if you don't completely redesign the engine, I think with the power output, if you don't triple the power output or the RPM, I think you should be quite fine. I don't know if you are used to change the rod stroke ratio or something like that because you need it, or it's just because you heard that it could be better, or
I think my take on it is those who sort of have heard of the concept probably put more weight into its importance for a modified road car engine than it probably warrants. I come from a Mitsubishi 4G63 background with my drag racing, and there's a range of variants of that engine. And for a start, it might be even worth just talking about how we might be able to change the rod-to-stroke ratio. As I mentioned previously, when you're stuck with OEM geometry, there's a limit to what you can do. But in that 4G63 world, there is a range of options, and one of them is to use the 4G64 block, which is the 2.4 litre block, and that's got a higher deck. It's a 6mm taller deck, normally matched with a 100mm stroke crankshaft versus the factory. And what we can do is put a factory 2-litre crankshaft in that 2.4 litre block, and then we can mate that with a longer connecting rod to get the deck height of the piston back to correct. And that's quite a common option with the drag racing engines that are going to perhaps rev to 10, 11,000 RPM. I've tried various combinations, and I haven't really measured a viable or significant difference on my dyno. I wouldn't say that my testing's exhaustive. Having said that, I probably also wouldn't run a 2.3 stroker, which is where we put the 100mm stroke 4G64 crankshaft in a 4G63 block, the shorter deck block, and you can get away with that by raising the wrist pin in the piston. So that actually makes your rod to stroke ratio worse than a 4G63 out of the box. Probably wouldn't rev that to 11,000 RPM, but that's not to say that people haven't done it. Might just not like it at 10,000, 11,000 RPM. It might not last that long, but yeah, that's my take on it. It's probably not quite as important. If you're designing a bespoke one-off engine that's going to rev to 12,000 RPM and you're not constrained by OE parts as much, then yeah, at that point, maybe that's a different deal. So that's kind of where I see it, but I'm also not an engine designer.
Yeah, sure. That's also my point of view. Let's say that it's not a parameter that if you get wrong, you destroy the engine or have poor results. It's some like fine tuning on the mechanical parts of the engine. So for the most people, I think it's not so relevant, or it's always yes, overlooked, and
Yeah. All right, moving on. Next one is bearing clearance. And again, this is a topic that's pretty fiercely debated. I think there's a lot of difference as well when you come from a modified OEM engine world to something that is bespoke and designed for a particular purpose. I will, despite using the metric system here in New Zealand, I will talk in imperial measurements of thousandths of an inch, just because that's kind of still our biggest market. And for me, the nice, easy one to always remember is that a sort of a good rule of thumb for oil clearances on the crankshaft is 1/1000th of an inch clearance per inch of journal diameter. So if we have a 2-inch journal diameter, we're probably going to find that the clearance should be 0.02 of an inch or thereabouts. Okay, so obviously when we're building an engine, we use the factory workshop manual as a reference. That's going to tell us the target clearance and the range of clearance that we can get away with, which is all well and good for a factory engine. Again, coming back to my 4G63 engine, we took what do they make, 350 horsepower off the showroom floor. Mine was at the end of its development closer to 1,300 horsepower, revving to 10,500 RPM. So to get away with that, the general direction that we go in the aftermarket is to build the engine with looser than stock clearances. And then that'll typically see a reduction in oil pressure because it's easier for the oil essentially to escape. So we kind of make up for that by moving to a slightly thicker, heavier viscosity oil. When we deal with sort of bespoke racing engines designed for that purpose, the general trend is to go the opposite way with a tight bearing clearance and a very lightweight viscosity oil for reduced frictional losses. I'm interested, can you give me your take on where you sit with oil clearances, their importance, and the general trend that you see?
Yeah, of course they are very important. They are fundamental for the engine life, let's say. And I think the rule of thumb is quite correct. We also use in a metric system 1/100 of millimeter each 10 millimeter of pin diameter. So it's I think pretty much the same on our engines. Yes, we are used to do that. Of course, if you can manage to have tighter tolerances and you are sure that the deformations of the components are controlled and are in some tolerances, you can go lower with the clearances. And what I think the approach of the aftermarket is that if you increase the power on stock parts, let's say, all the deformations and all the movements of the crankshaft and the block are higher than the stock ones. So you have to avoid the contacts between metals and you enlarge the clearances, I think, for that reason mainly. But also on the OEM cars, on modern cars, I think it's the opposite trend. So reducing the clearances as much as possible and reducing the oil viscosity. Now I think I've seen 0W8 on some Toyotas, and I think they are very very strict clearances. But you have to keep in mind that OEMs have a quite complex system of assembling the engines with different classes of bearings and everything, so they can reliable put the same clearance everywhere, and they can be sure that everything is working properly with that bearing clearance.
So you're talking here about graded bearing shells, so that depending on the minute tolerance differences between a journal diameter on a crankshaft and maybe the bearing tunnel and the block, you can choose the correct grade bearing to get that clearance exactly right on every bearing.
Yes, that's what they do. And so they can lower a lot the viscosity of the oil, so reducing the friction, reducing the fuel consumption and CO2 emissions. That's always the target now of OEM cars.
Of course. I guess you've got the flexibility, though, that unlike the OE manufacturer, and again, I'll come back to my 4G63 example, Mitsubishi are designing that engine with the intent of 350 horsepower and 7,500 RPM. So it's fit for purpose. The clearances are suitable for that. And when I take it to 1,200 horsepower and 10,500 RPM, it's not that. And as you sort of alluded to, you look at a crankshaft or an engine block sitting on the bench in your workshop and everything seems really rigid. But the reality is, under those stresses, the crankshaft probably resembles a bit of a noodle. So we're trying to build in that extra clearance so that we don't end up with metal-to-metal contact. That's not going to end very well for anyone. You've got the ability, however, to know exactly what your engine is going to rev to, exactly how much power it's going to produce, so you can design the components with the rigidity to not resemble that wet noodle at RPM, correct?
Yeah, we can do that. let's say we keep a safe margin on that, so we do not go as low in the clearances as they do in the OEMs, but we keep this the general rule of thumb of the a bit smaller than the aftermarket, because then, as you said, if you go wider with the clearances, you need much more oil flow, and the oil flow needed goes up very very fast with the clearances. If you double the clearance, I think the oil flow will become 10 times, not double. Yeah, so you have to keep in mind that
There's some negative repercussions with the increase in oil flow as well.
yeah.
I can only imagine that you aren't designing your engines to require custom bearing shells to be made as well. I assume you're designing around existing off-the-shelf bearings.
Yeah, yeah.
And how do you decide? How do you decide on what to use there? Basically, what I'm saying is, have you got sort of a known sort of range of bearing options from different engines that you've tested, proven they work? You've got the graded options as well, so you can set your clearances exactly right, and those are just what you design your journal diameters around.
Yeah. Let's say that for choosing the bearings, we start with all the constraints that we have. Usually, the constraints are the pin diameters, because the crankshaft has to be rigid enough and has to be able to withstand the power level of the engine. And so the diameters are pretty much the carrier of the bearing decision. Then you have the width of the bearing, in which you calculate the width by the maximum pressure that the bearing can take. So when you have the combustion pulse coming down, the combustion force applying on the bearings, you know which is the pressure on the bearing, and you can determine which is the most correct bearing. Then, of course, you have the dimensional uh, constraints. So you will have some maximum dimensions that you can fit in your design, and you have to adjust everything to make it work with all these compromises. But and you have to find the other important parameter that I'm forgetting, but it's not less important, is the availability of the bearing that you choose.
Yeah, it'd be real handy if you can actually get them.
Yeah, if you choose a bearing that on the catalog is present, but then it's not even no more produced because the engine is discontinued and no one buys them, you have made the wrong decision, because you cannot find them, and yeah, you don't have you don't have the bearings. So you have to take also that into account. Yeah.
Okay. All right, next topic, V angle. And again, something that we don't need to consider in the aftermarket, because you get what you get. You're dealing with a specific engine, and the angle between the bank of cylinders is set by the engine designer. You've obviously got more flexibility here, and I mean, you can set the angle between the banks essentially within reason wherever you want it, but there are some combinations that are common. For example, you know, if we're taking a V8, if we divide 8 cylinders by 720 degrees, we end up with 90 degrees, which is your typical angle between the banks. If you go somewhere else other than 90 degrees, we end up with an odd fire engine, which is not necessarily the end of the world. There are plenty of odd fire example engines out there. What drives your bank angle decision? Is this sort of just a packaging determination?
No, it's not just packaging. I mean, yeah, I think that okay, the first thing is the customer requirement, because sometimes the customer requires to have strange V angles. Maybe not strange, but strange for that number of cylinders. So, for example, the V12 4 turbos was requested to have a 120 degrees V angle.
Which would normally be associated with a V6 as well.
Yeah, to fit the hot V, so the turbochargers inside the V, to have the space for that. So that was customer requirement. But usually, yes, you start from the ideal degrees, and then you look at your constraints that you have to modify this V angle. That, for example, in V12, that you would have 60 degrees of V angle, but if you look on the market, all the V12 that are available are not actually 60 degrees, but they are 65, 70, because, for example, you need to make room for the intake trumpets.
Yeah, 60 degrees would be very, very narrow, wouldn't it? Making not a lot of room for anything between the banks.
So you have like 65 degrees, which is what we are designing right now, the our V12 naturally aspirated, to make room for other things, because we saw that going 5 degrees more than the 60 is not impacting the engine very much. It's not doing basically anything to this has practically no impact. Also on the sound, we saw that sound is not much affected by 5 degrees of widening the V. So we went with that. We have more space inside the V to accommodate direct injection, for example, and intake trumpets and ducts. So there are also always other things to consider, always a trade-off.
I'm guessing for a racing engine as well, a wider V angle is going to help reduce the center of gravity height, so that'd be beneficial.
Yeah, sure. A wider V angle, of course, pushes the engine down. If you go with boxer engine or 180 degrees V angle, like some old Ferraris, you have the engine sitting very low on the ground. So that's helping, of course. Yes.
Yeah, and I guess it's a trade-off as well, because then packaging constraints become problematic in a different way as well.
At the end, engineering is always a trade-off between a lot of things. So
Not specifically related to the V angle, but just as you mentioned, the hot V with the quad turbo V12. Is there sort of any pros and cons of the hot V configuration where the exhaust exits in the center of the V and the intake manifolds are on the outside, and vice versa? It's something we sort of tend to see a lot with European V configuration engines, and the opposite, I guess, with JDM engines.
hmm well, it's pros and cons. I think are not so driving. Yes, you can find some pros and some cons doing one thing or the other, but not particularly. Let's say if you design the car, the vehicle accommodating for a hot V, maybe it's then easier to design the exhaust line and everything going up. Maybe you want to design a car with the upper exhaust muffler, let's say, in the upper part. So there are many supercars, hypercars with they are doing that now. And so having the outside on the internal part of the V, you have the exhaust coming out straight to the upper part of the car, which is where you want to have it, or the opposite on the opposite way.
So essentially, it's not a engine design consideration; it's packaging for the application specific.
No, from what we've seen at the moment, no. It's for naturally aspirated. Yeah, of course, it's a constraint on the engine, because if you want to have a good airflow inside the engine, you need to have the air coming from the upper part, where you can also take it dynamically and going straight down to the engine. So it's the best for the natural aspirated. Of course, you want a cold V layout, but for a turbocharged engine, it's not so evident the advantage.
All right, moving on. Next one I want to talk about is the head design, and we've kind of touched on a little bit of this already, but more specifically, I wanted to talk about valve actuation methods. I'm going to go out on a limb here and guess that everything you're building is all 4-valve, but there's a variety of different methods of actuating the valves, some with their own pros and cons. Have you got your preferred method that you essentially utilize on all of your engine designs?
Well, let's say that we have different methods depending on the application. On lower revving engines, we use bucket lifters, so traditional bucket lifter that are quite simple, quite cheap, quite reliable, and everything.
Are these mechanical or hydraulic?
We use mechanical usually that are more simple, yeah, and much lighter. And but when you go up with the RPM and you want to have a very steep ramp on the camshaft, so opening and closing ramps on the camshaft, you need to have a very low inertias and you need to go to finger follower design. So basically, you have a finger with a pin, and the camshaft presses on the finger and the finger presses on the valve. So you have just the finger to move the valve, and it's much lighter than the bucket design. And it has its own disadvantages, of course, because it's much more difficult to set up for the reliability, and it's more costly because part need more different materials and different treatments and coatings to not wear. But for high performance engines, it's the best.
So as I understand it, the finger follower actuation's sort of the typical method in Formula One. Is that correct?
I think so. Yes.
Yeah. So essentially here, the finger follower, the advantage is the lower weight, lower inertia versus the bucket and shim style. Well, bucket is a one piece if it's mechanical, kind of to set the lash. Is there also limitations with the bucket valve actuation in terms of the diameter of the bucket versus the cam profile you can run on it?
Yes, of course, if you run with a very high valve lift, especially, and the lobe is very pronounced, you need to have a very good diameter of the bucket because you have to avoid that the camshaft work outside of the perimeter of the bucket because of wear and.
Yeah. I guess along with that, as you increase the diameter of the bucket by rights, the weight of the bucket is going to become greater as well. So you're sort of making more problems for yourself.
Yeah, greater as well. Also, the dimensions and everything on the head is becomes a problem. Yes.
Okay. You mentioned coatings with the finger follower. So can you talk to us a little bit about the coatings you use and how they work?
Yes, usually on the finger followers you have to apply a coating, so you have to use a very hard steel first of all, with tempered and everything, because he has to withstand the very high amount of pressure that the cam is pushing on. And on top of that, for wear purposes, you have to do the coating. So it's usually it's a DLC coating, so diamond like carbon coating. So it's a very thin layer, some microns of layers of very hard surface, like diamond hard. Let's say there are different hardness of these coatings, but the best ones are much come close to the diamond hardness. And so they avoid that the cam wears the finger, because it's a very big problem that. And also setting up the system in a way that it doesn't wear, it's not so simple, because also with the DLC coating, if you don't do things right, it can become a problem. A part of that comes also from oiling the surfaces. You need a good lubrication. Yeah, so we have sprays direct of oil directly on the camshaft's contact point with the finger, and that is crucial because we made a lot of tests on the cold test benches here to accomplish the target, because it's very difficult. Yeah.
Okay. As you're talking about this, I'm sort of thinking to myself again, I don't know why I keep coming back to the 4G63, but maybe it's what I know best. They use a sort of a roller rocker style valve actuation. Could you incorporate a roller into a finger follower, or is the mass that would add sort of make it detrimental?
Yeah, that's the mass would become much higher, because at that point, to accommodate a roller, you would need a much stouter finger, and it would be much heavier. I think OEMs do that for NVH because it's much more quiet than standard traditional cam.
So NVH, for those who haven't heard the term, noise, vibration and harshness, which is a very, very important parameter for OE manufacturers to make the car quiet, vibration free and just nice to drive. We don't care about that in a race car.
No, we don't care about. Yeah, sure.
The harsher the better.
Yeah, and they put the rollers so the wear is not a problem, and they are much more cheaper, all the parts.
Yeah. On that note, just in terms of wear, what's your sort of design life cycle between rebuilds on your engines? I'm guessing it probably varies between the different engines, but can you give us some idea?
Well, it depends, of course, on the engine, but for road use, let's say we advise a rebuild at, let's say, 20,000 kilometers for the Kimera engine. Let's say it's that kind of kilometer. Then for racing, of course, much sooner. Let's say some thousands you need to rebuild. Yeah.
I think my rebuild life cycle on my drag engine was about 4 kilometers, so that sounds pretty good to me. Actually, yeah, about every 10 runs down the drag strip, it was coming apart. Not always because it needed to, but always better to stay on top of these things than find out the hard way that you should have rebuilt it.
Well, 4 kilometers, I think, in drag racing is quite a long distance.
It was enough. It was enough. In terms of some of the other engine components, I'm just interested to find out about your piston design. Always, typically, you're going to find a cast piston inside those engines, which has the benefit of lower thermal expansion coefficient. Basically, it doesn't grow as much as it heats up, which allows us to set tighter piston to cylinder wall clearances. In the aftermarket, we usually throw cast pistons away and move to 2618 forged piston. Downside of that is that they do expand more, so we end up with looser piston to cylinder wall clearances when they're cold. This can result in noise at cold start and some increased oil consumption as well. What's your sort of piston material go-to?
Yes, we use forged piston in 2618 alloy, so it's the one expanding more. Let's say it's not a cast alloy. Yeah.
Are the problems with that if you want to achieve emissions compliance?
No, we didn't find it harder. I think you mean for oil consumption, maybe, or something like that.
Yeah, not an issue.
No, not an issue. For the engine emission test, you need to warm up the engine very quickly. So you design the first part of the warm-up strategy to run very, very fast to the operating temperature of the engine. So I think in 30 seconds, the clearance is already quite gone. Yeah.
Okay. In terms of life expectancy of these forged pistons versus cast, I'm assuming here that we're operating under conditions that the cast piston would also be able to support without failing. Is there a difference in piston wear and piston life?
No, I wouldn't say so. It's we saw that the also forged pistons with this kind of alloy is very durable. Is of course you have to design it very carefully with the correct thicknesses and everything, but they are very durable. I mean, we don't produce so extreme engines that we put them under extreme conditions, but I can say that they are very, very durable. Yes.
Okay. I'm interested, just sort of coming back full circle with the engine design and development process. A lot of this is going to be done in software simulation, as we kind of touched on earlier. I'm just interested, so once you actually get to the point of manufacturing an engine and putting it on a dyno, how well does the validation in the real world match your simulation?
Well, there are different stages of matching of things, let's say, because you first have the yes, simulations for the power, then you have the simulations for the resistance of the components, then you have the when you design the engine in the CAD, make the CAD model. It's basically like a simulation, also the CAD model, because you see the engine assembled, but you have to think about how it will be assembled in the workshop. And there they start to come out the discrepancies between the design and the reality. So also on the mounting, some things don't work. Let's say maybe a screw is impossible to screw on, something like that. Don't not major things usually, but you start already on the mounting phase. And then on the dyno, well, I think we are within the 5 to 10% in the worst cases, but in the 5% behavior of the engine on the simulation is correct. I mean, for the power delivery, yes. If you start looking other things, as we said before, knock control and other things, that's much more difficult. But power-wise, as we said, it's the most easy thing to to obtain at the end.
In terms of sort of prototyping and validating the engine, are you going through a process of maybe building a single cylinder to test, or are you committing to an entire engine? I'm just guessing that it'd be quite an expensive process to build an entire V12 to prototype and test.
Yes, actually, at the moment we've always done the first one good, let's say. So we started with building the complete engine and testing it directly on the dyno. The correct way would be to make a single cylinder and to test it and to improve it on the single cylinder. But you need, of course, time, money, and on the projects we did up to now, we did all the improvements, let's say engine by engine. Let's say that we do some tests before on the cold test rigs. Like for example, we have a flux bench where we can measure the flux of the cylinder heads, which we 3D print some samples before of a single. That's the single cylinder. We 3D print a single cylinder ducts part to test on the flux bench, for example. Then we can test the camshafts. So we make a single cylinder camshafts rolling on the bench to see for breaking parts or wear or wearing of the parts. We can test oil pumps. We can test a lot of components, let's say.
So you've got the confidence essentially to take that out and then build the entire engine and know that it's probably going to do what you want.
Yeah.
Even when it comes to production, though, we were speaking before we started recording. I think you said your production is sort of in the range of maybe, was it 10 engines per year?
Yes, in the 10, yes, some dozen a year, so 20, 30, depends on the project, but that's the kind of numbers we are talking about.
Yeah, but we're not talking hundreds or thousands of engines. So the consideration I sort of would have there is the technique that you're using for manufacturing the blocks and the heads. Generally, in production terms, these would be cast items, but that process, I would say, doesn't lend itself that well to short or low production runs. The other option which we see in the aftermarket is billet components, which have their own sets of pros and cons. You are using casts, so how do you sort of navigate that process with low production runs?
Yeah, well, the cast is the most difficult parts on the engines are the one casted. This is very true for the low production numbers because making a cylinder block, but also even more the cylinder head is very very difficult to achieve it in a short number of pieces, the correct design of the piece. not as much for the cylinder block because it's quite simple, let's say, because it has not a lot of internal passages, a lot of internal cavities, and it's much more open. And but for the cylinder heads, it's a very demanding task to design a correct part to have it cast right at the first trial. And to do that, usually we go with rapid prototyping casting. So nowadays it is made with 3D printed sand molds. So you can 3D print one piece and have it cast, and then look at the result, and then improve it on the next piece. Of course, it's always a bit of trial and error, but it's much cheaper than building the molds for the traditional process.
Okay, so rapid prototyping you're using for the production of every block and cylinder head casting.
Yeah.
Okay, and this is a technology I can only assume wasn't around, I don't know, 15 years ago. Like that wasn't an option, so you couldn't really be operating how you are now back in that era?
Yeah, well, back in the era, we didn't actually produce the parts ourselves. So, like 20 years ago, we didn't produce engines in their complete form, but we were more like preparing the cars for racing. Yes, so vehicle preparation. Now that we have to build the engines from scratch, we see that the task is much more difficult than it can appear to a person looking from outside. And the technology has come a long way since also 10 years ago. I don't think that 10 years ago you could 3D print the sands, and I don't think it was so widespread. But nowadays for prototyping, also OEMs do that way, so it's very popular.
Yeah. I don't know if it's possible for you to give some numbers around this, but I'm assuming that if you were in mass production, thousands of engines, it's obviously going to end up being significantly cheaper once you've rapid prototyped and you've proven your proof of concept to then go about actually having the patterns and molds made for conventional casting. Do you know if there's where the crossover point is, or the number of engines you'd have to be producing for that to make more sense than rapid prototyping?
I think you are in the range of some hundreds of engines to take advantage of the steel molds that you have to make, and the tools, yeah, and the studies and tooling. Yeah.
I guess ultimately, to a degree for you, it probably doesn't matter too much. The additional cost of the rapid prototyping just gets passed on in the unit cost of the completed engine.
Yeah, I hope in the future we sell a lot of our engines that we are developing now, so we can swap to traditional process of casting, and that would be quite good to hit that target. Yeah.
Yeah. All right, Riccardo, I think we'll move towards wrapping this up. And of course, we've got the same three questions that we ask all of our guests at the end. And the first of those is, what's next in the future for you in Italtecnica?
Well, for me now, I think I'm in a very good position, and I'm very happy about that. Now that what I've done in these 5 years that I've been here for the company, I think we are also going quite well because we are growing. Now we are 25 people, but when I came here, we were like 15, 16. And then this type of market really went well, and we managed to jump out of the box, let's say. And so in the future, I think we will improve that in that kind of market, and we switch also in the supercar hypercar market, which we are entering now with the for example V12 4 turbos. It's equipped on the hypercar, so we are entering this market, and we see good possibilities now because we are offering the engine with homologation, so emission compliant.
So exciting times ahead.
Yeah.
All right, second question. Is there any advice you'd give to a younger version of yourself to help reach where you are today in your career faster? And I mean, you're 30, you're pretty young. It seems like that's tracking along quite nicely, but still, any words of wisdom you can give us?
Yes, I would say that to search for what you are looking for. Let's say not just go somewhere because you think you are not worth more, or just being happy with also of a position that you don't really like. Just aim for more, and also change company, change environment if you think you are not worth if you are worth more than what they are offering you. And of a younger version of me, I would say maybe work even more than I did to reach this position faster. But I'm quite happy on what went on in these years. So I would say that I would replicate it, and it would be enough, yeah, for me.
Yeah, sure. And I think the upshot of that is similar to sort of how I view things, though, is if you do something that you love, something you're passionate about, the old story, you'll never work a day in your life. Now, that's not always entirely true. I love my job, but there's still great days and days that maybe are not as great. But, I think you spend so much of your life working, you might as well be working at something that you're passionate about and you enjoy. The tricky side to sort of keep in mind is you also need to be doing something that has some economic value. In other words, something where you can actually earn a decent living as well. But that's something that's not that easy to navigate all of the time. All right, our last question for today, Riccardo. If people want to follow you and see what you're up to, how are they best to do so?
Yeah, of course, we have social accounts on Instagram. You can follow us at italtecnica.engineering. You can find us. We upload weekly some posts or stories or reels. Instagram gives you a lot of possibilities. And then you can also check our website at italtecnicaengineering.com, and where you can find all what we do, and all our experience, our projects, and basically everything what we are doing, who we are, and you can get in contact with us. Also on Instagram, we are very user friendly. You can write to us as you basically did. It's completely fine for us.
Yeah, it worked for us. That's how we got you here.
Yeah.
As usual, we'll put links to those accounts in the show notes to make it easy for people to find. Look, Riccardo, it's been great speaking to someone with a level of knowledge on engine design and development that you've got. Certainly, I imagine there's a lot of information in there that everyone listening is also going to have benefited from. So thank you very much for your time today.
Thank you to you, Andre, and to your team for this interview and opportunity. We didn't expect it because we consider us still quite small, and you are well known in the field. So it is a very pleasure for us to.
No, our absolute pleasure. I hope you've enjoyed this episode of Tuned In, and don't forget, by using the code podcast500 at checkout, podcast listeners can get a huge $500 off our VIP package, which includes over 40 current courses, as well as a long list of courses to be released in the future. As a VIP, you'll also get lifetime access to our members-only webinars and our community forum. Lastly, we'd love it if you could drop a review on your chosen podcasting platform. These reviews really help us to grow our audience, and that in turn helps us to continue to get more high quality guests. To say thanks, each week we'll be picking a random reviewer and sending them out an HPA t-shirt free of charge anywhere in the world. This is also a great place to ask any questions you might have too, and I'll do my best to answer them if your review gets picked. So this week, a big shout out to Dayton from Florida in the US, who has said, this podcast is the way to stay motivated and keep your build going. I can't believe the amount of detail that's packed into every episode has given me the desire to want to learn more about all of the topics that have been discussed. Well, great to hear that it's giving you some inspiration there. And if you reach out with your t-shirt size and shipping details, we'll get a fresh tee shipped straight out to you. All right, that concludes our interview. And before we sign off, I just wanted to mention for anyone who's been perhaps hiding under a rock and hasn't heard of High Performance Academy before, we are an online training school and we specialize in teaching a range of performance automotive topics, everything from engine tuning and engine building through to wiring, car suspension and wheel alignment, data analysis, and race driver education. Now remember, you've got that coupon code. You can use podcast75 at the checkout to get $75 off the purchase of your first course. You'll find our full course list at hpacademy.com/courses. Important to mention that when you purchase a course from us, that course is yours for life as well. It never expires. You can rewatch the course as many times as you like, whenever you like. The purchase of a course will also give you 3 months of access to our Gold membership. That gives you access to our private members only forum, which is the perfect place to get answers to your specific questions. You'll also get access to our regular weekly members webinars, which is where we touch on a particular topic in the performance automotive realm. We dive into that topic for about an hour. If you can watch live, you can ask questions and get answers in real time. If the time zones don't work for you, that's fine too. You're going to get access as a Gold member to our previous webinar archive. We've got close to 300 hours of existing content in that archive. It is an absolute goldmine. So remember that coupon code podcast75. Check out our course list at hpacademy.com/courses.